Well, as the chair didn't introduce me, I'm going to get let's wait for my presentation. So, while trying to understand, using data from the Califa survey, the star formation histories and the metallicity distribution in these galaxies, but today, as I only have 10 or 12 minutes, I'm going to talk about a little project that we are trying to do, and is to study the evolution of the metallicity gradient using integrated stellar populations. So the scientific motivation for this came from the work by Gibson and Allen, and also, well, Princeton a year earlier, where they saw that the majority of hemodynamical simulations of these galaxies, or Milky Way type galaxies, I don't know what I did, the problem is to get rid of this. Oh. So while the majority of hemodynamical simulations reproduce the present metallicity gradient of galaxies like our own Milky Way, which is around minus 4.4 kiloparsecs, the evolution with redshift could be very, very different. And he saw that this evolution depends mainly on the prescription of the stellar feedback that you put in the simulation. So he ran like two identical these galaxies in simulations, varying the prescription for the stellar feedback. The one with normal feedback, you obtain a very steep metallicity gradient, high redshift, and then a strong evolution. And the one with an enhanced feedback, but you also put some radiation present from the massive stars, predict a flat metallicity gradient and high redshift, very mild evolution. So we thought that it could be a very nice constraint for this poorly unknown stellar feedback in simulation. So we thought, okay, let's gonna try and see if we can measure this evolution of the metallicity gradient. So this has been tried to do before, using basically two methods. The first one is in our own Milky Way, mainly using stellar tracing with different ages, like OB stars, planetary RGB stars, etc. And the results are contradictory, so some groups predict a flattening with time, and some predict a steepening of the metallicity gradient with time. There is very difficult to age date these tracers when they are older than 2 years, so that's a problem. Another problem is to estimate distances. There's some people have tried to do that as well in galaxies in the local group, but outside our own Milky Way. And there's a very recent reference by McGreen et al. This year, and they obtained different results for different galaxies. Another, in principle, more direct way to measure the evolution of the metallicity gradient is to study the metallicity gradient in galaxies at high redshift. And with this, measuring the metallicity in the ionized gas using N2H alpha tracer. And again, the results are contradictory and different between different groups. So some people have found very steep metallicity gradient in some galaxies, in a few galaxies. And some found flat or even positive metallicity gradients in other galaxies. Here the main problem is that when you have a poor spatial resolution, you tend to artificially flatten the existing metallicity gradient. So in fact, it was claimed that those studies finding very steep metallicity gradients were the only ones that were reaching very high spatial resolution by measuring the gradients in lens galaxies and with adaptive optic. Okay? However, in the last few months ago, this study came out also with a much larger sample of lens galaxies and also with adaptive optic, and they are claiming that while there are some galaxies showing a very steep metallicity gradient, the majority were showing like flat, very mild metallicity gradient as well. So I think, again, we still have to enlarge the sample and understand what's going on here. We don't know yet how the metallicity gradients in high-redshift galaxies are. So we propose here a different approach, which is tracing the metallicity gradient of stars with different ages using galactic archaeology or stellar populations in integrated spectrum. So to do this, well, what I'm going to present here is just for a sample of 82 phase-on these galaxies using the Califa survey, although we are enlarging the sample now. And to measure star formation histories and metallicity relationship, we use a stack map. I don't have time to describe the code, so you can ask me later if you want. But I'm going to show you a little bit how it works. So if we want to measure the metallicity gradients for stars of different ages, we have to prove that we can measure the age-metallicity relation from integrated spectra. So this is some synthetic star formation histories that we built. This one with double bars, and this one a truncated star formation histories, and with different age-metallicity relations. And so the solid blue bars are the synthetic values, and the yellow balls are what we recovered with the stack map. And so you can see that in principle the stack map is working well. Of course, it's always easy when you use the same models to build the star formation histories and to recover them. So we are trying to now do this with real galaxies by comparing the star formation histories and the age-metallicity relationship that we obtain with result extrapolation using color magnitude diagrams, and with that we obtain by obtaining an integrated spectra over the same region. And so here, in a result that we promised last year, now we are doing this with other galaxies in the local group. This one is in the Large Magellan Cloud. So those are the fields of the HST where we used to build the color magnitude diagrams, and the blue region is where we can to obtain the integrated spectra, and those are the results. So this is the cumulative mass flux compared to the edge obtained with the color magnitude diagram in blue, and with the stack map in red, so you can see that they agree pretty well, and the age-metallicity relations. So this result giving us confidence to do what I'm going to show you now, which is those are the galaxies from the Khalifa. We were mapping the galaxies and obtained this output, so the mass fraction versus age, flux fraction versus age, and the age-metallicity relation. And what I'm going to do is to obtain the mean metallicity in different age ranges. Okay, I'm going to show the metallicity weighted values here. So this is just some examples, so you can see it will be the metallicity gradient for all populations, intermediate, young, and including here the age to region, which we also include in the comparison. I'm just going to show some results. This is the differences between the metallicity gradient of the old population versus the young population, the difference in the slope. This is an histogram of the values. So the majority of them are in the negative region, meaning that the metallicity gradient for the old population was steeper in the past than it is now. Of course, it may depend on the mass of the galaxy. This is in fact an advantage of using this method with respect to the other method that I told you before, that we can use a large sample of galaxies covering a range of mass and other properties. We have a lot of different properties, but because it's a short talk, I'm only going to show you here the difference in the slope of the metallicity gradient between the old and the young population or intermediate versus the central velocity dispersion. So that's a proxy for dynamical mass. And in principle, you may think that it's kind of a trend. So the more massive galaxies have a steeper metallicity gradient systematically. Steeper metallicity gradient in the past, but for the less massive galaxies, maybe you can get both behaviors, no? Steeper or flatter. Now that I'm adding more galaxies to the plot that I'm showing here, what happened is that for this mass range, you obtain galaxies with so very negative values in this difference, so with very steep metallicity gradients in the past. So maybe for this mass range, you can find galaxies showing unseparated here. And that would probably put into agreement the discrepant results of high redshift, but we have to look at the properties of those galaxies in more detail. So now we can get a mean metallicity gradient and assign them redshift. I mean redshift as a function of the age interval that we are using, and make this plot. So as you can see, we are finding like a real trend. So galaxies at high redshift showing steeper, more negative metallicity gradient than galaxies at low redshift. But if you look at the scale of the metallicity gradient, the evolution is very minor. And in fact, if we put the points in the plot that I showed you at the beginning of the talk, in the predictions by Gibson et al., you can see that our points are compatible with those models in which with those models with an enhanced feedback. Okay. And well, this is compatible with two recent studies that I mentioned before, one using resolved extrapolations and one using measurements at high resolution galaxies. So in fact, plenty of time because I'm finishing now. So this is the summary of my talk. We are studying these set of collisions in a sample of in these galaxies from using data from the Khalifa survey. We are finding clear trend but very little evolution of the metallicity gradient. So that is compatible with those cosmological models with enhanced feedback. I have to say, I haven't mentioned that, it's very important, that of course what we are measuring is the metallicity gradient as it is today. The first that with the first method with the results of stellar populations. If there's been dynamical evolution in the galaxies, for example, if the stars didn't remain what they were formed because they were radial migration or other kind of processes, we are not actually measuring an evolution in the metallicity gradient. We are just measuring a lower limit. Okay? But still, I think these measurements would be valuable to actually constrain the amount of radial mixing by comparing the results with those obtained in high-redshift galaxies. So I guess we have to also put some efforts to obtain larger sample of gradients at high redshift to complete this study. Thank you.
That's a good example of a good speaker. Let's stick to the time. So, okay. Questions? Wow. Okay. Sorry. The denominator in a gradient is delta R. And delta R now is not what it was in the past, and we don't know what it was in the past, right? So you compute the gradients of all populations at their current location, not where they were 6 gigayears ago. Right?
Yeah.
So, of course, we cannot do that with archaeology or anything, but the modelers can do that. When you do the prediction, you can make a metallicity gradient as where the stars are nowadays. Okay? Metallicity gradient at 60 years ago, but consider the stars where they are nowadays. So that might be a good idea to suggest modelers to produce predictions, in ways we can test them.
Yeah, the thing, I mean, it's true. It's not perfect. I mean, the thing is that the cosmological summing simulations, predictions, normally they produce these that are a little bit too hot compared with these that we observe in real life. And you get a lot of mixing due to numerical fitting, which is not real. And those simulations which are idealized, they normally, I think, overestimate the amount of radial migration. I mean, and it's very dependent on the simulation, so which one do you believe? But I think in that case, because they put some asymmetric structures that are too strong compared to what you observe in real galaxies. And they usually don't put any volts at all, and etc. So it's not straightforward to do that comparison that you mentioned.
Okay, just short, very short, brief question or not? If it's long term. Okay.
In the simulations, the enhanced feedback is. What do you mean by enhanced feedback in the simulations? And I guess that you are not planning HN feedback, yeah? It's only start.
I think that's right. I mean, Brad is over there and he's the one with the simulation, so maybe he's the right person to answer. But I think the difference is that he put a radiation pressure for massive stars on top of normal supernovae feedback. And we are always talking about stellar feedback, yeah, not HN.
Okay.
Is that right?
Okay. We don't have more time. Thanks again.